So now we're ready to talk about what that atom is actually made of and how the different components are arranged. The different pieces of the atom come in three different types. The proton, uh, and the neutron, which are similar to one another in that they have about the same mass. This is the mass in grams, this is the mass in atomic mass units. For the purposes of the test, I just want you to remember that protons and neutrons have about the same mass. We just call it an atomic mass unit of 1 each. They differ in a property called electric charge. The proton has a charge of +1, and the neutron has no electric charge at all, so a charge of 0. The other thing that you need to know for the test are these symbols. So the symbol for a proton comes in three types, P+, or H+. We'll tell you a little bit more about this later, why H+. And then the neutron is given by the symbol N, or N with the superscript 0. So again, these superscripts are meant to identify the charge of the two types of particles. The third type of particle is called the electron. So it's given by the symbol E or E-, and it has the same charge as a proton, but opposite in sign. The other thing you should know is that most of the mass of the atom is tied up in protons and neutrons because the electrons hardly weigh anything at all. In fact, the electron is 1 divided by 1,837. That fraction is the fractional mass of an electron relative to a proton, or 1/1837th the mass of a proton. So again, most of the mass of an atom is tied up in protons and neutrons. Now, let's look and see how these three different particles are arranged. So here's a picture of this. The protons and neutrons occupy this, a space right at the center of the atom, and it's very tiny. So here we see what we call a nucleus, where the protons and neutrons are. We see 4 protons and 4 electrically neutral neutrons. Now, the electrons are out here in space. They're called an electron cloud. It's sort of the region where you will find the negatively charged particles. They have so little mass that they tend to be moving very fast, way faster than these heavy particles. So they're out here moving around in some sort of complicated motion. Now, the other thing that I want you to have some understanding of is the relative size of the nucleus to this total size of the atom. The nucleus is 10 to the minus 15th meters in diameter, and the size of the atom is 10 to the minus 10th, so that the difference of going from 10 to the minus 15th to 10 to the 10th is 10 to the minus 10th is a factor of 10 to the 5th. In other words, this is 10 to the 5th times bigger than this value, right? If we added 5 to minus 15, you would end up with minus 10. Well, that's equal to 100,000. So what we're saying is that the overall size of the atom is 100,000 times bigger than the actual size of the nucleus. So the size of this nucleus is not on scale. It should be so tiny you really wouldn't even see it on the screen. To give you another perspective on this, if you blew up an atom to the size of a football field, about 100 meters, from here to here, the size of the nucleus would be 1 millimeter, which is about, if you take your thumb and your index finger and you look at it, you try to get them as close as possible, that's about 1 millimeter. So that's where the nucleus is, and then the electrons are somewhere outside of that, between there and 100 meters, or the size of a football field. So that means that the atom is mainly empty space. So that's something that you should remember. And sometimes you'll see these old school pictures, right? So there are lots of problems with this picture. First of all, the nucleus is just way too big, right? The other thing is that the electrons do not move in planetary-like orbits. Okay, it's an old type of picture. You should just be aware of it. Now, what is causing the negatively charged electrons in the cloud here to be bound, really, to the presence of the nucleus? Well, we have positively charged particles in the nucleus, and the electrons are negatively charged. Opposite charges attract. So this is the electromagnetic force that's causing the electrons to be bound to within the vicinity of the nucleus. The other thing that you should know about the electromagnetic force is like charges repel. So negative charges repel from one another, and positive charges also repel. So let's talk about the negative charges repelling. One of the reasons why the electron is mainly empty space is because the electrons are repelling one another. Okay? So they're trying to get as far away apart as possible. Now you might be wondering, well, if positive charges repel, why are they attracted to one another in the nucleus? Well, the electromagnetic force does lead to a repulsion between the positively charged particles here, but there's another force that's causing the nuclear particles, the neutrons and protons, to be bound tightly, and that's called the strong nuclear force. And it is much, so there should be a space here, strong space nuclear force. It is much stronger than the electromagnetic force. So that's what's causing these particles to be bound together. The other thing is some nuclei are more stable than others, and you need to have neutrons to space out the positive charges, because the closer the positive charges are to one another, the greater the electromagnetic force for repulsion. So that's one thing that the neutrons are doing, is sort of spreading the protons out apart in the nucleus. The other thing that you need to know is something called the mass number. It's given by the capital letter A, and it is always a whole number or integer. It's never a fraction, because what you're doing is you're just counting the number of protons and neutrons in a particular atom. So if you're just looking at one atom, you should be able to count how many protons or neutrons are in it. So in this particular atom, we have, at least from what we can see, we can't see on the back side, but from what we can see, we count 1, 2, 3, 4 protons, 1, 2, 3, 4 neutrons, for a total number of 8. So the mass number of this atom would be 8. Now, when we look at the information in the periodic table, each entry is an element, and each entry will have a number. So if you look in the periodic table, the elements are ordered, reading from left to right, going from the top to the bottom, in order of atomic number. This particular element is element 19, and the atomic number is given by the symbol Z, and it defines the number of protons in the nucleus. So the potassium atom has 19 protons in the nucleus. So that really is what defines an element, is the number of protons. The next piece of information you'll see is a letter. So this is the symbol of the element. K actually stands for the Latin kalium, which we call potassium in English. So you need to know that K represents the element name potassium. The other piece of information that you get is something called the atomic mass. Now, we haven't really introduced this yet. The units are in atomic mass units, and they are often a fraction. Do not confuse this with the mass number we just defined on the previous page, which is always a whole number. Now, how many electrons does a potassium atom have? Well, it has to have the same number of electrons as protons, because the atom is electrically neutral, meaning that the total charge on the atom is 0. If you have 19 positive charges from the protons, and then you add them to 19 negative charges for the electrons on the outside, when you add these two together, this becomes 19 minus 19, which is 0. Listen to my language again. I said that we're adding these together because we have 38 particles, and we are adding them together. It's just that the sign of the charge is different. This is positive, this is negative. So in terms of the arithmetic, we end up subtracting, okay? But that's just because of the consequence of the sign. You really should be thinking addition. We're adding the two types of particles together, and we're finding that we get zero electrical charge. In other words, the number of positive charges, when it equals the number of negative charges, balance out so that you end up with zero.